Hello everyone, and welcome to the fourth and final video of our series Linux Kernel Exploitation Return to Userland. Today in this video, let's see if we can escalate our privilege and obtain a root in the emulator. First, here is a quick recap. This is the stack structure of the function hackMeWrite. We already leaked the value of the canary in the previous videos, and now we need to overwrite the return address with the function that gives us a root shell in the userland. We know now that we need to write 168 byte in order to reach the return address. Here is another representation of the stack, but here I'm considering the data type of C. The reason for that is that we are writing our exploit in C, and here I'm using unsigned long. So I will declare an array that's of type unsigned long, and for the write buffer, for example, we need 128 bytes, so that means 16 and 8 here, that gives us 128 bytes. And for all the other variables, the canary, the RBX, all of them, they will be of type unsigned long. That makes overwriting the stack easier, so we don't go to any kind of misalignment issue. And here you see this is the first code snippet of our exploit, where here control return address. As you see here, I declared, as I said, a payload of type unsigned long. I give it a size, and here I'm using the index to access this payload. The index is the canary offset. We saw that from previous video as well, 128 divided by the size of unsigned long, that give us a 16. That's exactly what we have seen here. The canary is at index 16 here. So then I take the value of the canary, I put it in the payload. Remember again, because when we write the canary on the stack, the program check it and it is the same canary, so then we don't have any issue. Then we have RBX, RSI, RBB. We don't care about their values. And then here at index +4, this is the address of the function kernel escalation and return to user mode. Here where most of the magic happen, and we will see, we'll talk about it later. After that, when the payload is ready, you see I'm writing the payload on the dev hackme using the file descriptor. So this is the first function here. Let's talk now about kernel escalation and return to user mode. Remember, our vulnerable module runs in kernel space, and we need to escalate our privilege in user space. That means three things. First, we need to escalate our privilege in the kernel space, and then safely return to the user space, and there spawn a shell that gives us the root access. Let's go step by step. First, escalating privilege in the kernel space. The most common way to do that is by using these two functions: prepare kernel cred and commit creds. Prepare kernel creds, it create a new credential structure in kernel memory. If we pass null to it, then it returns a new credential structure for a privileged user. On the other hand, the commit creds applies the newly created credential to the calling process. And by the way, these two functions are legitimate kernel mechanisms used for authentication and privilege management. So now imagine if an attacker in the kernel space and manage to execute this sequence, commit creds and then prepare kernel cred with null, that means the process is root now. Okay, how can we use these two functions? We need to leak their addresses, And there are multiple ways to do that. For example, we can read it from the proc key, all symbols, but that require a root, and we don't have a root now. So the second way, we will do that using symbol object dump command. Let's go to the shell here, and the first command that I want to search for the commit creds. That's easy like that. It just give me, okay, this is the address of commit creds. And then I can do the same for prepare kernel cred. Then also I have the address for that. I should mention that by default, modern Linux system have a kernel space or kernel address space layout randomization, or KASLR, enabled by default. So which randomize usually the kernel addresses. But remember, we disabled this features at the beginning, or all the kernel protections at the beginning for learning purposes. That means now the addresses of the kernel function remain static across reboots. And that's why whenever I shut down the emulator and start it again, always the commit creds and the prepare kernel cred will be at the same addresses. Okay, let's go back to the presentation. We got the addresses of both of them now with us. Okay, what the second step now is returning to user space. Usually, a process in Linux runs in two different execution modes. Either in user mode, where normally the normal application runs there, or with a kernel mode, where the operating system or privileged code are executed there. In both scenarios, the CPU maintain a different registers for that, either for the user mode, whatever the program needs to use those registers, or in the kernel mode if for interrupt or for a system call or whatever there. So before we execute the kernel mode, we need to save the user mode state registers. So save the user mode state registers. What are those registers? The CS, or the code segment, then the SS, or the stack segment, then the stack pointer, then the flags register. So we need to save those registers, because remember, after executing in the kernel mode, we want to go back safely to the user mode. So here I created those global variables, and then I'm storing this value in those global variables. Okay. Now, how we return to the user space from the kernel space? We will use the interrupt return instruction. This instruction restore the registers and switch back the CPU back to the user mode. However, we need to manually prepare the stack with these 5 values in this correct order. So we need RIP, or instruction pointer, which point to the address to execute in the user mode. So here, when we are now already in the user mode, what do you want to execute there? And we have function for that. We will see it later. After RIP, then CS, then the flags, then stack pointer, and then SS. So this is, we need to do it manually. This is not everything. We still have one more step, which is the global segment. Also, we need, before even this is before calling interrupt return, we need to call swap GS, or swap the global segment, just to ensure again that we goes back safely to the user land. At the end, this is how the function look like. Maybe it's better if we look at it in the VS Code. Where is it? Here. So the user return or instruction pointer, we pointed to a function. I called it spawn user mode shell. And you see here, this is the address of prepare kernel cred. Now I move it to RAX. Then here we want, because we want to pass a 0, so I'm RDI with RDI, XOR RDI, that means we'll get a 0 value. And then I call RAX. RAX contains the prepare kernel cred. Then here, the next one, because now the return address will be in RX, so I assign RX to RDI. And then here, this is the address of commit cred. We put it now in RX, and then we call commit cred. This is exactly that we are, where is this slide? Exactly, we are doing this one here. Okay. Then after that, we call swap global segment here. Then we prepare the stack SS, SP, flags, and CS, and then instruction pointer. All of them pushed on the, you see the push, all of them pushed on the stack, and finally we called interrupt return instruction. That should takes us to the user land. Okay, we saw that we are now in the user land. Instruction pointer point to a function in user land, and this function is spawn a user mode shell. So here already, because if everything works fine, when you execute this if statement, get user ID should be 0. Then we go inside here, and simply I am calling the bin sh using the exec ve function. If didn't work, then we see here we are failed to root again a root. So these are all the functions needed in our exploit. Maybe let's go back to VS Code and have a final look on the complete exploit here. So as you can see here, this is the main function. We start by saving user mode registers first. Of course, here you see we open the device, a couple of global variables here. Then we save the registers, and then here the function that leaks the canary there. This function will be used once we are in the user space, and here the function which escalate privilege and return safely to the user space. And here it's the function when we control the return address. So this is the complete exploit. What we need to do now is we need to compile. Maybe we'll go back to the presentation just to show you the final steps. We need to compile it, and then we copy the compiled program to where the init file system, RAM file system there, and then we need to recompress. You remember, I think in the first video when we said once we get our exploit, then we need to recompress the file system in order to bring our exploit inside the emulator. So we need to do that, and at the end we should get a root access. Let's see that in action. It's always better to see that in the shell. So here it's the component or the content inside the init RAM file system. Here is when I'm writing the exploit. The only difference now, I have this prepare function which will compile and then copy the user land to the init file system, and also recompress the init file system. So if I did prepare here, you see it's it will copy to tells you like compilation is done, and then here it's recompressing the file system. So that means now if I list again the content here, I will see now Userland is here, which was not before. Now Userland here. Okay, then I go one step and then run our run sh. Maybe let me make this smaller here, this a little bit bigger, and now we are inside the emulator ID. Of course, we are still not root. Let's the content here. It's our exploit. Let's run our exploit. Everything runs fine. It says privilege escalation successful. Let's give a root access. When I type ID, you see now we are a root. Okay, I hope this series was helpful. I know if you are not familiar with the kernel space, user space, that might be a little bit not easy, but I try to simplify it, or the concept. We didn't use any protections now in the kernel. Maybe later, if I create another series or another video where I start enabling the kernel protections and see how we can bypass them. I haven't really decided yet on that, but at least now it should give you the basic understanding of how Linux kernel exploitation works once you have a vulnerability either in a kernel module or anything inside the kernel. So thank you for watching, and I see you in maybe next series. Ciao, ciao.